Section 2.9 is on page 188, talks about linear approximation and differentials. Let's get those out of the way. Linear approximation we already did. If I look at a sketch of a graph, y equal f of x. And what I would like, and this comes in many forms in different courses, if I look at x equal a, wouldn't that be the point a f of a? So what I'm gonna do, I'm gonna use an equation for this line as an approximation. This is, oh, I already said that, y equal f of x. So what I'm gonna do, I'm gonna say the equation for this red line is y minus y1 equal m into x minus x1. And what is m? Isn't m the slope of the tangent at this value a? If I have y equal f of x, isn't that f prime evaluated at a? And if I solve for this and move this to the right, wouldn't you say y equal f of a plus f prime of a into x minus a? Isn't that an equation of a straight line? Guess what? That's pretty much half of this section. Actually, a bit more than half. There it is. That's the big secret. So that's what linearization is. Nothing more than the equation of a straight line. Alright? And now what we're going to do, we're going to use that. What do we need? We need a point. And we need a slope. Plug it in and there it is. You could memorize it this way. You could just derive an equation of a line and everybody's happy. So I'm looking at page 192 and I'm looking at number 2. I have y equal f of x. Okay, well, that's a trig function. At x equal pi over 6. If I plug pi over 6 in, the sine of pi over 6 is 1/2. Find an equation or find the linearization. Basically, instead of using this, I want to find y minus y1 equal m into x minus x1. How do you find the slope of the line? You take a derivative. That is the cosine of x evaluated at pi over 6. That's radical 3 over 2. So throw that in there and you're done. The back of the book will have L of x equal, they would move this over, plus radical 3 over 2 into x minus pi over 6. There it is. Using a straight line to approximate a curve, a function that's not linear. And here we have another piece as well. This is a bit more work. Well, let's see how that works. I would like to take, oh, I didn't erase that part. I'll erase it in a minute. I would like to take x equal 3 and plug it in. Well, if I throw 3 in, I'm looking at 2 divided by 9 minus 5, 4, 2 over 1. So y minus y1 equal m into x minus x1. There it is. Or L of x equal 1 plus whatever the slope is times x minus 3. Of course, you could distribute that in and clean it up. Well, what do I need? I need the derivative. Can't I say before I get there, can't I say that f is actually 2 times x squared minus 5 to the negative 1/2? And f prime will be negative 1/2 times 2 times x squared minus 5 to the negative 3/2 times 2x. Isn't that negative 2x over the square root of x squared minus 5 cubed evaluated at 3? That is a negative 6 over a 3 in there. That is 9 minus 5. That's 2. Square root of 4 is 2. Cubed, that's 8. That is negative 3/4. And there it is. You could distribute those in and say the actual straight line approximation for this mess is actually negative 3/4 x plus 9/4. 9/4 plus 1 is 13/4, if you really want. But this is sufficient. Okay, differentials, that's really differential equations. Suppose y equal f of x. If I take a derivative, isn't that f prime of x? And the differentials, an approximate change of the y is roughly the change, the rate of change in the x times the actual change in the x. So I'll tell you what that means on a graph really quick. Keep in mind, if I'm looking at a curve, and if I would like to move from point A to point B, if this is y equal f of x, this idea comes back in 5C, a big deal, comes back in 3 dimensions. This is f of A, and this is f of B. And if I want to find the change of y with respect to x, that is y2 minus y1 over x2 minus x1. Based on what I have over there, that's b minus a, and that is f of b minus f of a. What we want this difference. What we're going to do, we're going to really draw a tangent at A. And notice how this works. That is, if you change a certain x, so those are the same, the change in y is right there. But what we're going to give, so that's this, what we're going to give, we're really going to report this to be the change of y. So if I take this and I blow that up just a bit, I have the blue line curve coming up, and I have the change of y is actually this. But since my red line is running tangent, what we're going to report, we're going to report this to be the change of y. So we are short. Basically, this right here is an error in my approximation. So that's why we're going to say this is roughly dy dx. Those are the same. You move the same distance in the x. But the y's, we're going to really say dy is roughly the actual change of y. Okay, I want to do an example really quick to elaborate on this. If I want to know what the square root of 27.8 is. So basically, I'm looking at a graph, and if I enlarge this, make it out of proportion, let's say this is some x, the graph runs up. Let's say this is 25, and let's say this is 30. So the answer that I seek is really 27.8. I want this y value. That's my answer. What I'm going to do instead, I'm going to pick 25 because I know the square root of 25 is 5. And to compensate for this difference, I'm planning on using the tangent line. Well, this is how it works. The actual change that I need is right there. But what I'm going to report, I'm going to report this to be roughly the actual change. I am off by a certain error. And let me show you how that works. So I'm going to say this is roughly, the point is 25. So if I put 25 in there, I'll get a 5. So I'm going to say here that, you know what? I know what this is. This is 5 plus delta y. But delta y would mean I have to use a radical, which is an irrational number. Instead, I'm going to say, you know what? I'm going to use five plus roughly delta y. Well, isn't y radical x? And delta x, aren't you moving from 25 to 27.8? right? So I'm starting at x equal 5 and I'm starting at x equal 25 and I'm moving to x equal a distance of 2.7 on top of that. 2.78. Right? Third time will be a charm. 2.8. So, this is going to be 5 plus. I'm trying to figure out what this is. Now, keep in mind, I don't want to approximate this. I'm not talking about a calculator. I'm talking about by hand. That's an irrational number. Well, I know that dy is f prime of x dx. dy, the derivative of a radical is 1 over twice the radical of x times dx. That is 1 over twice. And the square root of 25 is 5 times 2.8. This is 0.1 times 2.8, which is 0.28. So we're saying this is 5.28. In reality, if I get my calculator out and I figure out what the square root of 27.8, before I figure the answer, I expect it to be over because I'm giving an overestimate. And if I hit equal, it's going to give me at 5.27. 5.27. So the actual value is 5.27. It turns out that this right here is actually 0.27. I gave 0.28 over by 0.1 because of my rounding, but it's a good approximation if you ask me. And if I look at the next problem, it says find the differential dy. Well, dy is, it's really dy dx. That would be negative the sine of pi x. And if you cross multiply, that's negative the sine of pi x dx. That's called differential equations right there, what we just did. Evaluated at the following given points. So this is part A we did. Part B says evaluate dy. Well, let's see. dy would be negative the sine of pi times negative 0.02 and I'm sorry, 1 x. X is 1/3 times dx, which is negative 0.02, and dy would be negative the sine of pi over 3 is radical 3 over 2 times negative 0.02. That's a positive. This makes that a 1. So that is 0.01 radical 3 times pi. Right? Oh yeah, right there. There should be a pi there. Chain rule. All right.